Good morning, Academy for Advanced Studies. This is the actual chemistry version of our limiting reactant lesson for today. You are more than welcome to search online and find alternative methods of solving for limiting reactant. But due to, the complications of that we're in right now, I'm going to only just kind of show one method. The upside to this particular method is that it works in all situations, and it's really, 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 really similar to what we have been doing in class with our three-step stoichiometric conversions. So it makes it nice because you know kind of already what to do. The downside is, yes, you're doing an extra calculation, an extra, you know, conversion fraction setup, one extra little step, but it makes it nice because there is the consistency there. So just kind of some terminology. I used this in the last video, but limiting reactant or limiting reagent is the substance that determines the amount of product that can form. So this is key here in the fact that my limiting reactant, the thing that I run out of, marker, determines how much product we can actually make. My excess reactant is the substance that's not used completely up. So I actually have some of this left over. We will deal with the excess reactant and determining how much is left over with that in another video later. Later. So in a chemical reactions, you have to know the values of the two reactants that are known if they are known. So I know how much I'm starting with for two things, and I've got to figure out using my dimensional analysis how much product I'm actually going to be able to make. Whichever one makes the least amount of product, that substance that started that calculation is the limiting reactant. So the couple of things to know about limiting reactant is you can't just look at the starting masses to determine which one makes the most product. Because every substance has its own unique mass, its molar mass does come into play. So just because one substance has a larger mass or a smaller mass than the other does not mean that it's going to run out first. It comes down to the coefficients and their molar masses. Also, the coefficients, it's generally impossible just by looking at them to tell the limiting reactant. We tend to deal with smaller coefficients, and just because one has a 3 and one has a 2 doesn't necessarily mean that the 3 is going to run out first. So you actually have to do the calculations. Um, you have to also make certain that you're comparing the same substances. I like to use the analogy of an apple and an elephant. Though they're both living and they both grow, other than that, there's not really much relationship between an apple and an elephant. So when I'm trying to determine my limiting reactant, the easiest method is to convert them both to a product and compare them together. In a sense, I am answering two questions at the same time by doing this, so it does kind of help save some steps down the road. And when you're asked to find theoretical yield, so remember, theoretical yield is just a fancy way of saying how much we expect to make. When you're doing that, if you do the two calculation method, it makes it simpler because you're calculating theoretical yield in both situations. You just have to remember to look at and determine which one is the smaller answer. So that smallest answer is going to be your theoretical yield. Whatever started that calculation is your limiting reactant or your limiting reagent. Last but not least, just remember that your given masses, your starting quantities, are the first things that go into calculating your product. So your limiting reactant is the substance that starts every other calculation in these type of problems. So, two calculation version, as I said, it's nice because it's what we're used to doing. It is, yes, an extra one little conversion calculation, but it makes it consistent. So what we're going to end up doing is we're going to convert both into one of the products. Typically, you're going to be asked and identified which product, but if not, it doesn't matter. Once you've got them both into the same substance, you're going to compare the two. The reactant that produces the least product is the limiting, and you're going to use that to perform any other calculations. The reactant that produces the most product is the excess reactant. It's the one that's going to have some stuff left over. Now, I will actually still be utilizing the mole map here for those of you who have found it quite useful in setting up your conversions. If you've not been using the mole map, then just use the equality statements that we've been doing in class. So let's look at an example here. How do I know I have a limiting reactant problem? Well, unlike all the other problems that we have looked at so far, I'm starting with two masses. So we are starting with two masses, and that's one way that we're going to know that it's a limiting reactant. There is my balanced equation. It has coefficients so that I don't have to worry about it too much. So this one is asking to go from grams to grams. This is probably the hardest type of limiting reactant problem, and the fact that you are going from grams to grams. Remember, anytime that we have grams in our problem, we got to use the relationship that 1 mole equals the molar mass. So we're going to need to use our periodic table to find the molar mass of each of our substances um, before we try and do our conversion. So take a moment, pause the video, find your molar masses. So setting up my conversions, like I said, we're doing two calculations. We're going to do one going from grams of sodium phosphide to sodium fluoride, and then we're going to do a second one going from calcium fluoride to sodium fluoride. So I'm going to go fairly quickly through this. If we were to use our map, we would see that it would be a three-step conversion. And I know that my first thing I got to write is my given substance. So I start with the first one in the problem. I set up my conversions. So where did we get this 99 from? Well, it came from the periodic table. It was 3 NAs and 1 phosphorus. So when I'm setting up my mole ratio, remember we got to look at our coefficients. So for my first mole ratio, 2 is going to go on bottom because it's the substance I'm getting rid of. And 6 is going to go on top because that is the coefficient for my product. My last conversion has me going to grams of NaF. So my molar mass of NaF is going to be on top and 1 mole's on bottom. Remember, the beginning and ending conversions are ones for the moles, and the mole ratio is the only place that you use the coefficients. You do not use the coefficients anywhere else. So I'm going to set up the second conversion. Pardon me. This time starting with my CAF and going to my grams of NaF. So you'll notice that the nice thing is this looks really, really similar from one calculation to the next. So my molar mass is different because my substance is different. My coefficients are different because we're starting with something else. This time we're starting with the calcium fluoride going to this sodium fluoride. The only thing that would be consistent between the two calculations is this last piece or this last step because they're both going to the same place. So I have my two answers. One of these is my theoretical yield, and it will tell me my limiting reactant. So I look at my answers and I determine which one's smaller. Since this is smaller, this is how much sodium fluoride I will be producing. This is my theoretical yield. It's how much I would expect to make. The substance that started the calculation is the limiting reactant. Whatever started the calculation, my reactant is the limiting reactant, and the smaller mass is my product. So as I said, you are doing an extra calculation by taking it all the way to grams or liters or particles. You're doing one extra conversion, but it's nice because um, it's consistent. It's the same thing we've been doing with our three-step conversions. So let's look at a second example. My equation's going a little bit wonky, but same equation, different starting masses. So notice my first one, my sodium phosphide was the larger number, and it ended up being not the limiting. This one, my calcium phosphide is the larger number. Remember, I said earlier that you can't just look at your starting masses to determine which substances is going to be limiting. Each one of these has their own molar mass. They each have their own coefficients. So you want to set up the calculations, the conversions. So we're going to the same product. Nice thing with it being the same equation is this conversion looks exactly the same. So notice this time, this is the smaller mass produced. So this would be my theoretical yield, and my starting substance would be my limiting reactant. It would be the thing that runs out first.